Okay, so after a bit of a delay, thank you all for coming. My name is Craig Savage. I'll be presenting tonight at the Citizens Data Science Meetup, and the title of my talk is Inconvenient Mathematics, or Why Data Scientists Can't Give Ugly Ducklings a Free Lunch. Before we begin, a few disclosures. First and foremost, my phone is on flight mode. Is yours? Secondly, as you may have noticed, we had some technical difficulties at the start of this presentation. I hope to give you a code demo, but I am not 100% convinced it'll work. If it doesn't work, rest assured, this talk is being recorded. It will be up on YouTube. The code will be up on GitHub. The slides will be up on GitHub. And directions to all of those will be at the end of the talk on a slide. Third, this is sponsored by Microsoft, so thanks to Microsoft for hosting. And I have used Microsoft R in the demonstrations and for the problems that I'll be considering. But just to be clear, I have no financial interest in Microsoft. Finally, conversely, I am employed by Deloitte. However, tonight I am representing myself as a private citizen, so don't construe anything I say as being the official viewpoint of Deloitte. And for the final one, if you have any questions, please save them to the end. So first, introducing myself in this talk, who am I? Well, I have a rather broad education. I have a PhD in electrical engineering. I have an MBA. And I've kind of built my career as being on the boundary between the technical talk and the business. And I have about 20 years of experience. The last time I gave this presentation, it wasn't 20. Editing that up to 20 was a bit bittersweet. But I've worked in several different industries. I've worked in defense for the United States. I've worked in biomedical engineering, and I've worked in banking, primarily risk, credit risk, operational risk. A little bit of fraud, but primarily credit risk. And you may think those are very different industries, but as I take a step back and look at it in a more abstract sense, what really motivates me is having systems implemented. So I don't just want to build models for the sake of building models. I don't particularly care if I'm using the latest and greatest machine learning, blah, 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 blah. I'm more interested in having a measurable impact. So I want my work to get implemented and to be useful to someone, and that's more important to me than the academics of it all. So if I start by analyzing the subtitle of my talk, Why Data Scientists Can't Give Ugly Ducklings a Free Lunch. Let's start off with data science. What is data science? Who is a data scientist? Now, unfortunately, this is a term that gets bandied around a lot, but it's not entirely clear what people mean. Some people say if you're building dashboards, if you're reporting summary statistics, you're a data scientist. Others say predictive analytics is required to be a data scientist. Some say data visualization. Some say you need to be able to do everything. Perhaps you've seen some infographics about what it means to be a data scientist with lots of different pieces. For the purposes of this talk, I want to talk about solving two types of problems, regression problems and classification problems. And I hope that we can agree that one thing that unites all data scientists, as a matter of philosophy, shall we say, is that we look to data. So we're looking for evidence. We may disagree on what data to use. We may disagree on what problems we're going to solve with those data. But I hope that we can all agree that evidence should be preferred, or data over dogma. And if you try to do things without data, if you try to just use expert judgment or something, you may feel like this, that you keep throwing things at your target and your target has no idea. And it may even be that there are memes populating the internet about what it means to try to be a data scientist without data. So let's start by talking about data. What data am I going to use for this talk? So I went out and got some data from Kaggle. In particular, there's a data set about Melbourne house prices. It's public, you can go download it. It's got about 60,000 rows of 13 variables. So it's not what I would consider to be big data in a data scientist sense. And I want to talk about Melbourne house prices tonight. So I put some filters on these data. And if you're a data scientist, the first thing you're probably used to is get your data and then you need to filter it, clean it, define your target population. So here I've said, right, I only want houses, not flats, not townhouses, etc. I put some cleaning rules that you need to have at least one room fewer than 5 bedrooms, and that it's in Melbourne Metro. So I've excluded everything in rural Victoria. There shouldn't be anything in there because it's a Melbourne house prices data set, but again, if you're in data science, just because the data set says Melbourne doesn't mean everything is part of Melbourne Metro. So now I want to start off by solving the regression problem. I want to use that data set to build a model to predict house prices here in Melbourne. And then I'm going to look at a classification problem to see whether or not any individual house is a good deal. So these are the two types of problems I say I'm going to talk about tonight, and that I say define a data scientist. Can you estimate a value, a continuous value, a regression problem? And can you estimate, in this case, binary or discrete value as a classification problem? And so, starting off with a little bit of exploratory data analysis, these are some house prices. This is the distribution. On the near side, that's just the price. On the far side is the log of the price. And looking at it, you can see that there's this rather long tail in price, and the log of the price looks closer to normal anyway. It's still not normal, and if you look carefully, you can see that there are some outliers even in the log. And in the log, they pop out a little bit more. And on the full price, that low price ends up just in the first bin. And so here I'm going to be looking at the logarithm of house prices. Now I've used logarithm of house prices. I've used logit transformations, which are different from logarithms. I've used arcsine transformations. I've used arctangent transformations. I've used hyperbolic tangent transformations, square root transformations. And so whenever you're looking at your variable and you want to transform it somehow, the question you may ask is, but why? When you're mesmerized by all the mathematics, you should still be able to answer the question of why are you transforming it in this particular fashion, and more importantly, what impact is that going to have on your model? So starting off with regression, let's take an example. I'm going to model house prices, and I'm going to use 3 different models. The first says house prices are constant. Every house in Melbourne Metro is $1 million. Now, as a data scientist, you think this is really coarse, and you would never say anything like this. However, if you're talking to a friend, and they've asked you, well, have you bought a house? You're more than likely to say, no, a house in Melbourne is $1 million. This is what's called a common language model. I'm not getting into variables. I haven't looked at my training data. But in our experience, you may find it to be not unreasonable that a house in Melbourne is $1 million. So this is my first model. And then I want to build a linear model. Again, I've taken the log of price, and I'm going to say how many years ago was this sale? Was it within 1 year, within 2 years? What region is it in? North, south, east, or west Melbourne? Is it within 10 kilometers of the city center? And how many rooms does it have? And each one of those I've taken as a discrete variable. So you can enumerate all the combinations of those, and that's how many different house prices there are in that simple linear model. I can take it one step further, and I want to use a neural network, because neural networks are fun, and many people will say, if you're not using a neural network, you're not a real data scientist. Again, these aren't big data, but I'm going to use more granular features. How many days ago was the house sold? What suburb is it in? Not region, but what suburb? What's the distance from the city center to this house? So not is it less than 10 or not, but as a continuous value, how far is it to this house? How many bedrooms, bathrooms, and car spaces does it have, rather than lumping them all together? This gives me a much more granular model. And again, the data aren't particularly big, but I can build a neural network based on this. And in general, you can say that because I'm using a log transform, the log of the price is some function of my independent variables x, some coefficients on those variables a, plus random noise. And what I'm going to do is I'm going to take my Kaggle downloaded data, split it randomly into training and test, build a model, well, except for the constant model, which just says every house is $1 million, and I'm going to repeat this. And then I'm going to look at the variance of the error on my test set.
So as I said during the presentation, there were some technical issues and the code demo didn't actually work, so I wanted to take some time to go through what I wanted to say here in the comfort of my own home with everything working properly. So with the collection of your favorite random number seeds, if I just do the first one, we split the data into training and test, and then we fit a linear model to the data using the training data and this functional form to say which variables I want to use. Resetting the seed, there's then a second linear model, which I'll get to soon enough. You can see all this is quite fast. We can fit a neural network. Now this is a small neural network because I don't have big data. I'm only using 5 hidden nodes and 50 iterations, but you see it converging down to about 4.5%. And if you're not using Microsoft R, if you're using other packages, the general philosophy here is largely the same, that you call a function with the data you want to use to train the model and which variables you want to use, and those return model objects. You can then predict based on your test data by providing the new data and the model objects that you created previously. You can get predictions. With those predictions, you can then calculate some metric. In this case, I'm using the variance of the difference between my price, or the log of my price, I should say, and the predictions that I got from the previous step. And so even if you're not using Microsoft R, this should all seem fairly familiar, that you build a model object using your training data and some specific function. With that model object, you can then generate predictions. And then finally, with those predictions and the true observations, you can calculate metrics.
All right, so I do that. And I look at the variance of the error in my test set, and you can see a couple things here. First of all, the constant model doesn't do very well. The linear model does better, and the neural network does best. Something I would like to point out is my constant model still has variation in run-to-run of its performance. It wants to update Windows 10. And if you're a data scientist, you should be happy about this, that the neural network does best. And off you go, and you can go to your management and say, look at how well the neural network does. It's got an error variance of less than 5%, and it beats everything. This is great, and you've probably all had conversations sort of like this, that using advanced techniques, you can fit models pretty well. But there's a bit of a catch here that people don't like to talk about. And this is the point of my talk, that there's a lot of inconvenient mathematical issues that data scientists often aren't taught, and these aren't talked about. So let's talk about some of them. In general, I said that my price, or log of the price, is some function of some independent variables x, with some parameters a, and some random noise. So if that function was linear, then you give me the value of x. The a vector would have the slope and the intercept. You multiply x by the slope, you add the intercept. That's the estimate of your mean response, and then there's some noise on top of it. No problem. And I said in the beginning that we all agree that data are necessary to make decisions, but we might disagree on which data. Well, as I've done here, you can pick different variables. You can give it different structure. You can do different transforms to your variables. But in general, once I write this down mathematically and I say, let there be a function that defines house prices, this turns into more of a philosophical conversation, that there is some function that will define house prices. And we don't know what that function is. So we pick some functional form, whether it be constant, linear, the configured neural network, as you wish. And we don't know the independent variables either. And oftentimes you say, well, it's not that house prices are random, but rather I don't have access to the real independent variables. I don't have access to people at the auction, their hormone levels and brain activity. So because I don't have access to that, that's actually what's generating that random term. So I don't know the true functional form. I don't know the true independent variables, but let's just talk about that functional form for now. So I've guessed that function, but now I'm not looking at the difference between my observed value and the true function, but rather the observed value, which is that f plus epsilon, and my function, whatever function I'm going to use, which isn't the truth. And you can go to Wikipedia if you need help with the algebra, if you look up bias variance trade-off, and you get something like this. Now the first term is the variance of y. Once I say that my true function is random, I'm going to have some inherent variability in my process. If I end up getting an error, a variance of the error that's less than that, I've overtrained. You can't estimate a random process better than its inherent variance. And then I get these other terms. I get f minus e of f hat. Now already some of you might be a little confused because I've said I've picked my function and I've got this expectation there. What's the expected value of my model? And if you don't like expectation, I've got variance of my model there too. Now if you're a Bayesian, this makes sense to you because you understand that when I say I get coefficients A, actually there's a distribution of those coefficients given my training data. It's more than just point estimates. So when I said slope and intercept in the linear case, I don't just get a single slope and estimate, but rather I get an estimated distribution of my slope and estimate, which has an expected value, and a variance. So in canonical terms, sigma squared is commonly used for the variance. Then I get a bias, the difference between my true function, which I don't know, and the expected version of the functional form which I've picked, plus the variance of my function. So now I want to look at these results in a slightly different manner. I've randomly chosen 25 house prices. The x's are the true price, and the yellow are the results of my linear model. So these little things up here. The pink across the middle, that's the constant. It has no variance. It has considerable bias relative to the x's, but it has no variance because it's constant. I don't care how you split your data into training and test. The constant model says every house is $1 million. Now the linear model has some little width to it, and sometimes there's an outlier marked by a point on the box plot, but even that is so close, it doesn't do much. And while more often than not the neural network is closer, there's considerable variation in the results from my neural network. If you're randomly splitting your data into training and test, and you use that randomly generated, or randomly chosen, I should say, training data to build your model, then your model is random. It has a mean and variance. It's not normal necessarily, but if you're randomly splitting and building your model based on that random split, your model is random. Now, I've been a bit unfair because I keep saying neural network and linear model as if that's the only thing that differentiates them, but I'm using different variables between them, so it gets dark. So what I want to do is, when I built the linear model, I had these very coarse features. I was using region instead of suburb, etc. So now I want to rip out the region and use the suburb. And I'm going to do the same thing. I'm going to repeat the example. And here I have the total variance between my predicted data from the models based on my training data and the test data. And when I replace the region with suburb, the error comes way down on my linear model. So this is good. So I said earlier that my linear model had less variance than my neural network. I've now got the bias down, and if I go back to my original plot, where you see the linear model has this nice tight, it's hard to see now, this nice tight variation, I'm going to be good, because when I put in my second linear model, it's got more width to it. I can't do both. Even if I'm using the model that gave me less variance, once I change which features I use, suddenly the variance comes up again, even when the bias went down. And this is true in general. If you're going to use more granular data, if you're going to have more coefficients, then you get fewer data points. When I went from region to suburb, region had heaps of points. Suburb has fewer. You have fewer points. You're less confident in the average. You're less confident in the coefficient. When you resplit your data into training and test, you have fewer in there. The average changes. The coefficient changes, and you repeat the process. And again, when you're splitting it randomly, you don't know how things are going to go. If you take your data and get features that are too granular, if you want to re-divide suburb into, say, street, you may have points in your test data that aren't in your training data. How do you allocate them? And so you can get these diagnostics like outliers. If you saw the previous presentation from this event, they talked about a lot of ways to look at outliers, diagnose outliers, things to do about outliers. You can get confidence intervals, and you can use some regularization procedure in linear models. Now, oftentimes when people talk about explainable AI, they mean a quite specific problem, that you have a bunch of input variables and somehow those have mapped you to some point. And they say explainable AI is how did you get from these to that point? When I talk about explainable AI, I want these types of diagnostics. I want to get confidence intervals about the weights on my neural network. I want to be able to regularize my neural network. I want to be able to increase the bias to decrease the variance, or perhaps vice versa, as opposed to taking what I get. And if you look up bias variance trade-off, you might find an example like this. You get something similar if you look up precision and accuracy. And oftentimes, if you find this type of information on the bias variance trade-off, yes, this is a good illustration. Yes, it documents those concepts of bias and variance. But oftentimes, it doesn't tell you what does the target represent. What do the points on the target represent? And you may think, are you okay? Yeah. You may think, okay, each target is a model, and each point on there is the application of that model to an individual observation. But there's another way of looking at it, which I hope I've illustrated in my previous box plots, that perhaps each target is one observation, and all the points on that target are different realizations of your model based on how you split the training and test. So that while this may be the full 4 possibilities of high, low bias and variance, oftentimes you end up in cases where you can bounce between these two. And you can't lock into a single model that has low variance and low bias. And so you end up putting out fires and chasing your tail. As you decide that your model has too high of a bias, so you use more specific features, and then you track those coefficients, you track what's happening, and every month you get different coefficients. And because you're getting different coefficients, they would like some clarity, so you increase you decrease the granularity of your model to increase your confidence in the coefficients, and the bias goes up. And you end up in this loop. So having spoken a bit about regression, let's talk about classification. What happens if we're not trying to predict something continuous, but rather something discrete? So I'm going to take my input data. Now I don't have whether this is a good deal even defined. And as a data scientist, you may be used to, I get my input data, I have my target variable, I try to match my input data to predict that target variable. Here I don't have a target variable. There's a few cases where the same house was sold multiple times, and I can see whether the price has gone up or down, but for the most part, I don't have a variable which tells me whether or not any particular house was a good deal at its selling price. So in building this classification, there's a few main ways to do it. The first is you build a regression model and then threshold it, where you can say a house is cheap, average, expensive, whatever. Or you compare it to similar points, so things like hey nearest neighbors, give me houses like this. And there are other methods, but those are 2 of the main ones. And one way you can visualize this is often used as a decision boundary, where I have this example where from the upper left to the lower right are the red points, and on the other diagonal are the blue points. This is what's called the XOR problem, and I'll be getting back to it later. And you can see that for the 4 algorithms here, you can form decision boundaries where if you're kind of inside the upper left to lower right for a future point, you would call that red. And if you're on the other side, you'd call that blue. So again, back to the subtitle of my talk, Why Data Scientists Can't Give Ugly Ducklings a Free Lunch, there's something called the Ugly Duckling Theorem. And it's about data-driven classification. So if I know nothing about whether or not a house is a good deal, I'm just going to take all my independent variables and let them sort themselves out into clusters. And I'm going to touch it as little as possible. I'm just going to let it go and let the data tell me what's a good buy and what's bad. And the Ugly Duckling Theorem says you can't do this, that you need to pick your features. Again, this is an example from Wikipedia. I have my 3 ducklings, if you will. The one closest to me comes first. The one at the end is not white. And so with those 2 features, I want to see which of these is not like the other. And you look at the one that comes first and you say, well, that's a stupid feature. If you flip the order, then the other one comes first. And the requirement here is that they're all different. So I enumerate all the combinations of whether one comes first and whether it's white. There's 8 versions. If you look at these and imagine them as 3 bits, that's the numbers 0 to 7. And now I pick 2 bits. So I want to compare A and B. And 4 of them agree and 4 of them disagree. And if I want to compare A and C, 4 of them agree and 4 of them disagree. B and C, 4 of them agree and 4 of them disagree. From the data itself, I can't conclude which one of these is more or less like the other. When you think, well, okay, that's 3. Let's do 4. Write out the numbers 0 to 15 in binary. Pick any 2 bits. 8 of them will agree, 8 of them will disagree. And you can keep going, 32, 64, as high as you'd like. 2 to the 100th. Big data is 100 variables maybe. If you're patient enough to write out 2 to the 100th, binary, pick any 2 bits. 2 to the 99th agree, 2 to the 99th disagree. If you're going to classify different things, it requires someone to pick which features are important. And this is true even if you go up to infinite dimensional space. And you may wonder, well, what does that mean? Well, if you leave yourself completely unbounded, any 2 things, you can come up with ways that they're alike. You can come up with ways in which they're different. So for example, me and this. It's an infinite number of ways we're alike, and an infinite number of ways in which we're different. And you may look at it and be like, oh, you 2 are pretty different. Let's hear how you're alike. Okay, we both have mass. That mass is less than 100 kilograms. It's less than 101, 102. And you say, okay, that's cheating. That's cheating. Okay. The mass is greater than a gram. And it's greater than half a gram, quarter gram. You say, okay, that's still cheating. But you can do the same thing with any numeric variable. Mass, volume, density, age. Pick anything. You can set the upper limit and the lower limit. And we both agree. What if it's not a quantitative variable? Well, neither of us are hot dogs. So the famous hot dog, not hot dog classifier would say we're the same. And I can go through and enumerate all the things that we're both not. Both of us originate in the northern hemisphere. And you may think, well, there's a lot of things that fit into those. You're giving very broad brushes. Okay, let's get a very specific feature. There are very few things in the universe being recorded as part of this presentation, and we're 2 of them. Clearly, we must be the same. So when you go through and try to classify things, you need to be very careful about where you get your features, because you can find things that agree and that disagree. And if nothing else, if you're doing this on a computer, which variables are you using here? Whichever ones you stored, you've deemed to be more important. And in the age of the internet, it gets worse, because if I want to know whether or not at this point the 2 of us are the same or different, I can get weather observations from around the world, I can get any stock price you'd like. There's no stopping, well, okay, there is stopping, but I can go a long way to get variables that have no impact on whether or not this and I are the same. You need to use your judgment. So okay, I can't just let the data decide whether or not these houses are going to be good buys or bad buys. So I'm going to use my regression models, and I'm going to say, okay, using my model, I get an estimate for the true worth of this house, and I'm going to look and see what the asking price of the house is. And if the asking price is less, then it's a good deal, because if I say my house is worth 1.1 million and it's being sold for 900,000, well, there's 200,000 there. I should go out and buy the house. And conversely, if I think it's worth 1.1 and it's being sold for 1.2, nah, just leave it. So I've got three algorithms here. Which one is best? My constant model, every house is $1 million. The first linear model I went over in my neural network. Which one gives me the best estimate of whether or not a house price is a good deal? And, well, I've got three models. I can build an ensemble. Pick any two of them. If two of them agree, or three, go with the majority. Which means if a house price is less than $1 million, if either my linear model or my neural network say it's a good idea, or sorry, it's a good deal, then it is. But if it's more than $1 million, then the other two algorithms must agree. And you can imagine coming up with something, and if you're a data scientist and you talk to experts, you may imagine an expert coming by and saying something along the lines of, "You done got it wrong, son. I've been working in this industry since you was knee-high to a grasshopper, and all your fancy mathematical mumbo-jumbo ain't worth nothing. I tell you what, you use your ensemble model, you tell me what you're going to do, and I'm going to go and do the opposite." You say, "Oh, well, okay, sure." So I have the three models, my ensemble, and then I have what I'm going to call a contrarian, which says I take the ensemble and I just reverse it. Okay. And I can look at, based on my split into training and test, and I can get predictions for whether or not something's a good deal. And now I need to assess this. So this is what leads to what's called the no free lunch theorem, concluding my why data scientists can't give ugly ducklings a free lunch. So I'm going to simulate 10,000 classification outcomes. Again, I don't have a target variable, so I need to simulate it. And I'm going to compare the performance of those 5 algorithms, and I'm going to put the result on the same plot with some transparency so that you can really see how the ensemble and the contrarian separate, because they're opposites of each other. And I do that, and I get, do you see how they don't separate very well? What if I'll split them out. There's no practical difference. At which point you may be saying, okay, Craig, you simulated this. Tell me more about how you did it. And the main result of the no free lunch theorem is if you pick your results randomly, uniformly, the expected difference between the performance of algorithms is 0. In which case you say, okay, hang on. So you built your models from these independent variables. You get mappings from them to whether or not it's a good deal or not. And based on your model, you may use different variables, you may use different weights on those variables, but then to simulate it, you throw all that away and pick this randomly. Well, what did you think was going to happen? None of your models are going to hold up to something that's been chosen independently at random. That's what independently at random means. And now, if you're new into data science, and maybe this talk isn't what you were expecting, or if you're not a data scientist, and you've just come along to see what all the fuss is about, if you get nothing else from this presentation, let it be this. If you're going to criticize something, be prepared to propose and defend an alternative. Because I agree, using uniform data isn't the best way to evaluate my models. But then what is? And here's where it gets inconvenient, because your first thought is, well, what do you mean? I've got a model. I'll use the constant model as an example. If it's less than $1 million, it's a good deal. If it's more than $1 million, it's not a good deal. So I generate that, and when I run my performance data, hey, the constant model matches perfectly. That's the best model. You can throw out that linear model and neural network. And that's true no matter which model you use. If you use your model to generate your predictions and see if they match, they do. So what should I use? And you may think, well, use one of the models. That doesn't work. Use a combination of the models. Well, that's the ensemble model. It wins now. You may think, okay, so give your data to a third party, hire a consultant, for instance. Let them build a model completely divorced from you so that it's a fair comparison. It's still being built on the same data set. Even my constant model of saying a house is $1 million, while it's not directly based on the data that I loaded from Kaggle, it's still based on my experience living in Melbourne watching the housing market. It's not that far off. The median is about 1.03 million. So when you're talking about these things and you're trying to assess your model, how do you do it? And speaking of the same data set being used in different ways, I said earlier that you may want to look at the variance of your model in a cross-validation. If you have a high variance model with the coefficients bouncing around, which one do you pick? Well, the no free lunch theorem says it doesn't matter which one you pick. If you don't have a reason to prefer any model over the other based on the expected statistics of your future data, you can pick the model from your cross-validation that did the worst. I normally pick the one that did the best, not because I think it's the best model, but because it's easier for me to convince my stakeholders that I'm using the best model that I found, rather than the worst one. And also referencing my earlier talk, let your data decide. If you think all this sounds funny, go try it. When you run cross-validation, take the model that did the worst, take the model that did the best, generate your new values uniformly at random, and see which one does better. If you're doing a binary problem, try what I've done here. Read in your data, build your model, reverse it. Make a contrarian approach. Assume your model is perfectly wrong. Generate your new values uniformly at random and see which one is better. And you may think, well, Craig, that's nice. That's a good example of how to demonstrate the no free lunch theorem, to build my model and then take the opposite and see nothing happens. But this idea that the end result will be completely opposite of what my model says, that never happens. Actually, there is a phenomenon called anti-learning. And that sometimes your training data can mislead you. And there are some examples of this. I mentioned the XOR problem earlier. And there are some examples from biology where you have big data sets, but you don't have many people that you've collected data, but then there are thousands of points or more for each person from whom you've collected data. And the illustration works like this. Here we have the XOR problem where I have the yellow circles and the blue triangles. Pick any point. Let that be your test data. So the three points closest to me, the two blue triangles and the yellow circle, it's my training data, and I build a classifier, and I get something like that. I missed my test point. In fact, there is no line that will separate these things clearly. And you may think, well, okay, there's no line, but I don't need to use a line. I can build a model with a disjoint decision boundary, and hey, look, I got it. My decision boundary puts a circle right there, even though it's not in my training data, and when I run my test data, look, it works. Nailed it. That may seem somewhat cynical, but even something that looks better like this. If you don't know that point is there, why does your decision boundary look the way it does? When I was introducing classification and I had this graphic, what if all these points aren't in your training set? Yes, each algorithm is capable of building something to discriminate them, but what if you don't see those data? Shouldn't you get decision boundaries more like that? So in summary, when I'm talking about classification, if you try to do things purely data-driven, it doesn't always work. You need to be careful about which variables you're using, and you can't let the computer do them automatically. Even if you're doing something like k-means or fuzzy c-means, you still need to specify in which dimensions are you building your clusters. If you just chuck everything in, who knows what you get. And modeling unseen data gets inconvenient. If you use your model to predict it, it'll match your model. If you say it's uniform, the no free lunch theorem applies. And of course, there's a space in the middle where you say, okay, I'm going to use my model, but then I'm going to add some noise to it. Sure, how much? If you add a trivial amount of noise, then you're using your model to verify your model. And if you add a large amount of noise, the no free lunch theorem applies. But if you say, well, okay, I'm going to add noise, but not so much that it breaks, well, now you're designing your test so that it passes. It's not really a test. And anti-learning happens sometimes. So if you're ever going through a classification procedure and you run your test data and you find out that your model's performance is worse than random guessing, your first thought will probably be, oh, I've got a bug in my code. I must have flipped it somewhere. But I encourage you to take the time and go through what's happening. Double check your code. Rerun it on your training data. Note that anti-learning is a function of the data, not of your algorithm. And it may be that you have these problems and you go through a bit of a war with your data, trying to build the optimal classifier. And people might not understand what it is what you're doing. But if you're generally well-liked and seen as somewhat magical, you might not need to explain anything. So in conclusion, I've gone through some of this inconvenient mathematics, as I was saying. There's the bias-variance trade-off, that by trying to minimize the error in your model, by adding complexity, you end up increasing the variance of your model. The ugly duckling theorem loosely says that you need to pick the features yourself. Purely data-driven doesn't always work. And the no free lunch theorem says generalized performance of your model can be very hard to estimate. And there's a couple of challenges that arise from this. The first is performance versus interpretability. And the second, which is a bit more philosophical, is does your model define the metric, or do your metrics define the model? And so I touched on these briefly. If we talk about performance versus interpretability, a common comment you'll get from management when you build a model that you can't necessarily explain is that I'm going to assume that my future data is like past data. And I might not know what variables are important. I might not know how they're distributed. I'm just going to say future data will be like past data. The ugly duckling theorem says there's an infinite number of ways in which tomorrow will be the same as today, and an infinite number of ways in which it will be different. And now if people say that, there's a trap. A common second statement to this is if the model is working, then I don't care if you can't explain it. This is logically equivalent to the contrapositive, which then says if people care you can't explain it, then the model's not working. It's not the same as if the model isn't working. Do you care if you can't explain it? And sometimes the answer is no. If the model stops working, who knows what happened? Maybe one of your competitors did something. Maybe your data supplier did something. Maybe something else happened and whatever. Rebuild the model, retest the model, re-implement the model, and move on. That's fine. Now this other question of does the model define the metric or the metric define the model? When I'm building models, I can take data and build a linear model that I think is appropriate without any test data. I can look at the coefficients, are they positive or negative, and I can go through with very little future data and build things on an expert level. I can even do that with no data. You can go out and ask the experts. If a house is this big, how much is it typically worth? And you get a lot of variation, but you can build models from the ground up with no data. So the first question is, does the performance on the test data define which one is best? If you're used to Kaggle competitions, the answer is yes. That's the only thing that matters. Is your performance on the test data the lowest or the highest or whatever the metric is the best? In industry, it's often not necessarily. Do you have the skills to implement it? Do you have the skills to monitor it, to maintain it? Does the regulator care whether or not you can explain it? The largest philosophical problem I have between myself as a data scientist and other data scientists is, can you tweak the model based on your test data? So you run your test data, you get an answer you don't like. Can you go back and change your model? And everyone shakes their head no, but if your cross-validation shows you a large range and you pick the model that did the best, did you use your test data to pick the model? Or did you know which model you were going to use beforehand? In my opinion, your test data is kind of a dress rehearsal for running your model in production. So you get everything ready, you run your test data, you have all your stakeholders in the room, you say, okay, we were expecting a 10% improvement and it came out as 15. Okay, pop the champagne, we all win. What if it comes out as 9? Do they say, 9's close to 10, fine. What if it comes out as 2? And all the awkward conversations that you can imagine having based on your test data before real money is involved, now try imagining them when you've had your model implemented for the first month. And what assurance do you have that your model is useful? I'm a firm believer in the kind of cliche that all models are wrong, some models are useful. So how do you know your model is useful? And this gets more complicated once you start introducing business metrics. And I'll leave you with a real world example. Here we have a history of budgets from the Australian government. And on the y-axis we have wage price increases. And the different colors are different budgets and their projections. And this includes under both Labor and Liberal governments. You can see that all the projections are kind of different shapes. But the one pattern I want to talk about is there's only one number where predicted is less than actual. Now, is there a reason why people might like actuals to be higher? Well, I'd like it if wage increases were up higher. I think the electorate would like hearing about how wages are forecast to increase quickly. And in fact, if wages are increasing, then incomes are increasing, then income taxes are increasing, and then we can promise more things to the electorate. And I don't know what methodology they're using here, or if it's changing since I'm getting different shaped projections. But if you're using a ARIMA model, or a vector autoregressive model, or a linear regression model, or a neural network, or some segmented neural network with fuzzy logic applied as to which one to use, or whether your expert says, I reckon it'll be about like that. How do you assess which one of these models is best? So, where you can find me? You can find me on LinkedIn. Past data and future data imply that I don't bite and that I can be bribed with coffee. So the colors aren't coming through the best. This talk and my previous talks you can find on YouTube, and this presentation and then the code will be up on GitHub after I get all the technology here sorted out. So some acknowledgements. First of all, thanks to Microsoft for hosting this event and for Microsoft ML Server. Thanks to Kaggle for the data, all the kernels, and the community. If you haven't been to Kaggle, aside from the competitions, which are kind of famous, there is an excellent community there. I recommend you go and look around if you're looking for any tips. If you'd like to start using Python or R or any other thing, there's lots of examples with code and English documentation. And, of course, for all the GIFs, jiffy.com. And to all of you for your attention, thank you.